Hello everyone, today I will present our study titled Azo Dyes derived from Eugenol Synthesis and Textile Applications carried out in collaboration with the Department of Chemistry at the University of Minho and CITES. To begin this presentation, I'll briefly introduce the context and next main goals. The textile industry plays a crucial role in producing materials that are not only visually appealing but also functional and adaptable to various needs. However, conventional dyeing processes are known for their high consuming of water, energy, and chemical substance, which result in considerable environmental problems. These methods also generate toxic effluents that often contaminate natural water sources, raising serious ecological and health concerns. As a result, the search for more sustainable and eco-friendly dyeing technologies has become increasingly urgent to ensure a cleaner, safer, and more responsible textile sector. So, the replacement of synthetic dyes with natural compounds has gained attention due to their lower toxicity and also the low environmental impact. Eugenol, carvacrol, and thymol, found in essential oils, exhibit antimicrobial and antioxidant properties, making them potential precursors for the synthesis of azo dyes. Azo dyes represent the largest class of the dyes used in the textile industry to their vivid colors, chemical versatility, and stability. Although these natural compounds have been widely studied in the last years, such as in pharmacology, medicine, and food preservation, research focused on their application in textile remains non-existent or very limited, particularly in the case of carvacrol and thymol. In this context, our goal was to synthesize azo dyes derived from eugenol, that is a natural phenolic compound extracted from clove essential oil. We chose eugenol because it is renewable and has functional groups that facilitate azo bond formation. After synthesizing the azo dyes, we characterizing them using standard techniques to confirm their structure. Then, in the second phase, we applied the dyes on fabrics using exhaustion dyeing and coating methods. Also tested their washing and light fastness, analyzing color change with the CEA lab system. Next, we present the results and discussion. First, starting with the synthesis of Eugenol-Derived. Synthesis of the azo dyes 3A and 3B was achieved via a classical deazotation coupling reaction. Initially, 3-amino-benzoic acid and 3-amino-4-methylbenzoic acid were subjected to deazotation under acidic conditions using sodium nitrite at low temperature between 0 and 5 degrees Celsius to form the corresponding disonium salts. Next, these disonium intermediates were slowly added to an alkaline solution of eugenol, acting as the coupling component. The electrophilic aromatic substituent between the disonium cations and the activity aromatic ring of eugenol led to the formation of the target azo dye. The crude products were isolated by vacuum filtration, washed with cold distilled water to remove inorganic byproducts, and further purified by flash column chromatography, affording the pure dyes 3A and 3B as solid materials. In the proton NMR spectrum of type 3A, we first observe a signal which corresponds to the benzylic group next to the aromatic ring. This is followed by a singlet confirming the presence of the methoxy group. Then we have signals which are characteristics of the vinylic protons. In the aromatic region, signals that confirm the presence of aromatic protons form the benzene and phenolic rings and showing that the aromatic system was preserved during the synthesis. Finally, we see a singlet which is attributed to the phenolic group and an additional signal further downfield that corresponds to the carboxylic acid proton. The spectrum confirms the incorporation of all expected functional groups, supporting the successful synthesis of the target dye structure. Now, looking at the proton NMR spectrum of dye 3B, we can see that it is very similar to that of the dye 3A. It shows the same characteristical signals in the aromatic, vinylic, and phenolic regions. However, one important difference is the appearance of an additional signal, which is consistent with a methyl group attached directly with the aromatic ring. This confirms that the dye 3B has a structure very close to the dye 3A, containing all the same functional groups with the addition of a methyl group as expected. The analysis of the carbon NMR spectrum of type 3A clearly confirms the presence of the expected structural unities. We observe signals which correspond mainly to the aromatic carbons from the benzene and phenolic rings. This confirms that the aromatic structure was preserved during synthesis. It is important to note that part of the signals associated with the allyl group also fall into this region due to their unsaturated nature of this side chain. In the aromatic region, the quaternary aromatic carbons, those not bonded to hydrogen, are highlighted in red in the spectrum, making them easily distinguished from the protonate aromatic carbon. Finally, a distincting signal is attributed to the carboxylic acid carbon, confirming the presence of the benzoic acid in the molecule. Overall, these results demonstrate that all the expected functional groups were successfully incorporated into the final structure of type 3A. Well, the carbon NMR spectrum of type 3B shows a pattern similar to that of the type 3A, with an additional signal confirming the methyl substituent. Following the methyl signal, we observe those corresponding to the methoxy and methyleno groups. Next, we observe the region where the aromatic carbons of the benzene and phenolic rings are located, as well as from the allyl groups, and also the quaternary carbons marked in red. Finally, a signal is attributed to the carboxylic acid carbon, confirming the presence of the benzoic acid unit. This overall sequence of signals confirms the structure expected of the dye 3B. So, while NMR spectroscopy provides detailed information about the proton and carbon environments in the molecule, future spectroscopy complements this data by identifying the functional groups present. The intense bands located between 1680 and 1700 are attributed to the stretching vibration of the carbonyl group of the carboxylic acid. Also, the presence of the azo bond is evidenced by bands between 1500 and 1600. The structure of the compounds were also confirmed by electrospray ionization mass spectrometry (ECA-MES) performed in the negative ion mode. So, after confirming the synthesis of the dyes, they were applied to cotton knit fabric by exhaustion dye. We tested two concentrations of each dye, 1% and 2%, both in their impure and pure forms. The dye bed was prepared with sodium carbonate and sodium chloride using a liquor ratio of 1:20 and the different dye concentration. Each dye process was carried out in a Matisse Labomate machine at 60 degrees Celsius for 60 minutes with a heating gradient of 1 degree Celsius per minute and 25 rpm. After dyeing, the fabric samples were washed with warm water, then dried, and finally submitted to color fastness tests to evaluate their performance. Now for the color fastness validation test. Light fastness was evaluated by exposing part of the fabric to direct sunlight for 3 consecutive days, and washing fastness was tested at 40 degrees Celsius for 30 minutes using phosphate-free detergent (ECA). The color changes were rated using the grayscale, ranging from grade 1, where is no strong what is strong color change, to grade 5, where is no color change. Also, the EL, A, and B coordinates were also recorded to describe lightness, L, and chromaticity, A for red, green, and B for yellow, blue. Well, the results of the textile application by exhaustion. Starting with the color strength, values show that samples dyed with impure form have higher color intensity than those dyed with pure form, especially at the 2% concentration. This suggests that impurities may improve dye fixation, possibly by facilitating interactions between the dye and the cotton knit fabric. Samples dyed with impure forms also showed lower lightness, indicating darker and more intense colors. On the other hand, the chromatinaceous showed positive A values that indicate red tones, while the B values reflected yellow tones, both contribution to greater color saturation. About the concentration, with 2% resulted in higher intensity and lower lightness than those with 1%, confirming that increasing dye concentration in the dye bed leads to stronger coloration regardless of the purity. After confirming the application of the dye to the cotton fabric, washing and light fastness were evaluated. These results showed low washing fastness, ranging from 1 to 2 on the grayscale, with no difference between the pure and impure forms of the dye 3A and 3B. This may be attributed to the nature of azo dyes and the absence of fixative agents during the dye process. On the other hand, fly fastness ranged between 2 and 4, particularly Di3B in its impure form showed superior performance compared to its pure form. For Di3A, the life fastness was equal in both pure and impure forms with a value of 4. These finds indicate that despite the intense color achieved, dye fixation during washing needs improvement, possibly using mordants or optimizing dyeing conditions, while the light fastness so promising for applications with limited sunlight exposure. In addition to exhaustion dyeing, the application of the dyes by coating was evaluated, which allows controlled deposition of the dye directly into the fabric surface without immersion. For this purpose, a coating formulation was prepared containing the dye, a bio-based polyurethane, aqueous fixer, and thickener. The paste was applied into cutter knit fabric using the knife-on-roller method with the layer thickness ranging from 0 to 0.2 millimeters using a Matisse level cutter machine. After application, the samples were dried at 100 degrees Celsius and thermofixed at 150 degrees Celsius to ensure adhesion and durability of the coating. Now the results of the textile applications by coating. Color strength analysis showed that thickener layers lead to stronger colors for both pure and impure forms. For dye 3A, the impure form had higher color strength values, reaching from 2.12 at 0.2 millimeters, while the pure form only reached 1.12. For dye 3B, the pure form performed better with 1.60 at 0.2 millimeters compared to the impure form. In conclusion, more thickness means more color, and performance varies depending on the dye and its purity. For the dye 3A, the impure form performed better, while for dye 3B, the pure form showed greater color strength. Light and washing fastness were evaluated for the coating application as done for the dyeing process. Compared to dyeing, the coating methods gave better washing fastness, especially when the layer thickness increased. With pure dye at 0.2 millimeters, washing fastness reached values between 3 and 4, while in the dyeing it stayed lower between 1 and 2. Impure dyes also improve with thicker layers, even though they started with lower values. For light fastness, coating gave lower values overall between 1 and 3, and didn't change much with the thickness. In contrast, pure dyes in dyeing showed moderate light fastness reaching up to the grade 4. Therefore, coating improves washing fastness compared to dyeing, but light fastness remains limited and dependent on dye purity. Finally, the conclusion and future perspectives. In conclusion, Eugenol-Derived Dyes 3A and 3B were successfully synthesized with the presence of essential functional groups conferred by various spectroscopy techniques. In both exhaustion dyeing and coating applications, the impure dyes resulted in higher color intensity as indicated by increasing color strength values. In terms of fastness, dyeing showed better performance under light exposure, while coating provided improved washing fastness. For the future work, it is proposed to investigate the role of impurities in dye fixation, evaluate the use of fixation agents, optimize the coating formulation, and also enhance light fast. Finally, it is essential to test the process on a larger scale, assessing its application to different fabrics and its technical and environmental viability. Next is presented the reference. Finally, I would like to thank everyone who contributed to or supported this work, and thank you all for your attention.